If you remember from a few videos ago, we talked about two different kinds of bonding. We talked about covalent bonding, and we talked about ionic bonding. So those two different kinds of bonding will give us two different kinds of molecules. If we have a molecule that is covalently bonded, that is going to give us what we call a molecular compound. These are two or more covalently bonded nonmetals. And again, the key here is the nonmetals. We can only have nonmetals in these molecules. If we have metals, then it will have to have ionic bonding. Metals don't do covalent bonding. So we're going to have only nonmetals in these kinds of molecules. The basic unit of molecular compounds is just the individual molecules. It's pretty straightforward. The basic unit of water is just H2O. The basic unit of dry ice, which is carbon dioxide, is just CO2. So that's pretty straightforward. Ionic compounds are a little bit different, though. So ionic compounds, as the name implies, are made from molecules that are ionically bonded. So this is a metal and a nonmetal. Not just metals, that's a whole different ballgame. It is a metal and a nonmetal, at least one of each in the molecule. You can have more than one, but you have to have at least one of each to have an ionic compound. So this consists of a cation and an anion. The cation is almost always a metal. There's really only one exception to that, and that would be this polyatomic ion, which we'll see later on. That's really the only exception. Every other cation is going to be a metal, and the anion is some nonmetal or some group of nonmetals. So it would be another polyatomic ion, as we'll see later. So it's multiple atoms that make up a single ion. When we're looking at ionic compounds, and we're trying to figure out what the formula of that ionic compound must be, the key to working that out is that the molecule must be neutrally charged. If the molecule is not neutrally charged, then it's not a molecule. By definition, molecules have a net zero charge. If you have a charge, then it's an ion. It's not a molecule. So, the positive and the negative charges must be equal. So we're going to balance these compounds. We're going to balance the charge of these compounds with subscripts. So the example that we're given here is magnesium chloride. Now you might be thinking, where do we get this +2 and -1? Those just came out of the blue. No, they didn't. They did not come out of the blue. If you remember, again, from a few videos ago, we talked about how with the periodic table, let's see if I can find it back here. I believe it was in this chapter. Yes. So we said that everything in this column is +1, everything in this one is +2, +3, -3, -2, -1, and then this is, these are just not going to make molecules. And then this column usually is +4. The metals, anyway, will usually be +4, but we can't always count on that. The main ones that we can count on are the -3, -2, -1 here for the nonmetals, and then +1, +2, and +3 here for the metals, especially aluminum. We can count on those being true. So we do know what the charges on those monatomic ions are going to be. And that is where the +2 and the -1 came from here, because magnesium is in the second column and chlorine is in column 17. And so we get the charges for those from the periodic table. So because the molecule needs to be neutrally charged, with +2 from the magnesium and only a single minus charge for the chloride, it's going to take 2 of the chlorides to balance out the charge. So we'll have +2 from the magnesium, 2 -1s from the chlorine. That will give us 2 - 2, which is 0. And so that's where we get Mg Cl2. 1 magnesium, 2 chlorines. And so we can do this with any combination of metal and nonmetal that we come across when we're trying to figure out the structures of ionic compounds. So let's look at a few other examples here. And actually, I want you to try and work these out yourself. So go ahead and pause the video here, and using just the atoms that are shown here, try to figure out what the structure would be, which is really just essentially figuring out how many of each of these atoms would be present in these particular ionic compounds. So go ahead and pause the video and give that a try. Alright, I hope you paused the video and tried to work that out. So, sodium and fluorine. Sodium is in the first column, it's +1. Fluorine is in column 17, it's -1. So they each have the same charge, just opposite in sign. And so this structure is just NaF. You just need one of each, because having just a single one balances it out. Calcium is in the second column, it's +2. Bromine is in column 17, so it's -1, just like the fluorine. And so because we don't have the same charge for each, we are going to need more than one of at least one of these, and that would be the bromine. The calcium is going to give us +2, and it's going to take 2 bromines to balance that out. Next one here, we already know calcium is +2. Sulfur is in column 16, which is going to be -2. It wants to gain 2 more electrons to be like argon, I believe, the noble gas argon. And so once again here, we have the same charge. So it's not 1 and 1 like it was before, now it's 2 and 2, but that's okay. They are the same charge, and so it is just CaS, calcium sulfide. That's what that would be called. Strontium is in column 2 as well, or group 2. Phosphorus is in group 15, so it is -3. This one's a little bit different now, because we don't have the same charge. We have +2 and -3, but we're going to need more than just 2 of one of those atoms to get this to balance. The quick and dirty way to always get these things to balance is take the charge for each of the ions and swap those as subscripts for the opposite ion. So take the 3 for the phosphorus, give it to the strontium, 2 from the strontium, give it to the phosphorus, and that gives us 6 for each. And that is the smallest charge possible, but it's the smallest number of atoms possible, while still getting an equal amount of positive and negative charge. Alright, and by the way, if you do this, the vast majority of the time it will work out. The one situation where it sometimes won't work out, let's say if you have some atom X that has a charge of +2 and some other atom Y that has a charge of -4, if you swap them like that, so again, take this and put it down there, that one put it down there, technically you will still get something that is balanced, but we always want the smallest number possible, and since both of those are divisible by 2, the actual correct answer would be x2y, since that's still balanced, but with smaller numbers. And so this would be the correct answer. So that's really the only time where just swapping the numbers like that doesn't give you the completely correct answer. Like, it's still correct in that it is balanced, but it is not the actual correct answer, because the actual correct answer is the smallest numbers possible that give you that balanced charge. Alright, so then the last one here, +2 for magnesium, -3 for the nitrogen. Same thing as the ones above. Mg3, N2. Gives us plus and -6 which is a neutral charge. Alright, I thought I was going to jump into the nomenclature in this video, but I think I'll actually save that for the next one. So we'll go ahead and finish this video here, and in the next video we will get into the nomenclature, which we will certainly not finish in the next video. It'll probably take 2 or 3 videos at least to get through the nomenclature. So we will see you there.